Alright, so this is lecture 27, which is on the change of variables for multivariate integration theorem. And I'm actually going to start with just kind of an example, kind of abstract example, but let's just look at how it would go for 2 dimensions and a region which was sort of natural to polar coordinates. In particular, I want to see how we could set up an integral of a function of 2 variables over this region, which I'll call R. So R is this kind of sector from R min, which I've from R min to R max. So this is R min in here, and R max is out here. All right, and so we have R min less than or equal to R less than R max, and theta min less than theta max is a description of this region in polar coordinates. And I think the natural thing to try then is to sort of break it into subsectors, right? Each one of which has the same change in angle or change in radius. So I'm going to take delta R in this case to be, oh, did I say 4? Oh man, that's supposed to be a 3. Because I have, my picture has 3. No, I got 43. That's even worse. Let me fix it. So just for the sake of illustration, I've made 3 radial bands, right? And I've made 7 angular bands, if you will. And so the area of the ijth sector will be 1/2 of the difference in the outer radius minus the inner radius squared times the change in theta. I had a pi here before, sorry about that. But anyway, Ri plus 1, so like you could see that here. The area of the 2/1 sector would be 1/2 R3 squared minus R2 squared times delta theta. That's the formula for the area of a sector, which you can see from like taking the difference of the area of the larger wedge versus the smaller wedge. If you want to look at the, anyway, I'm not going to get back. You can ask me an email about how to explain that if you want. But anyway, so R sub I plus 1. R sub I plus 1 is R sub I plus delta R. And so when we calculate the difference in these, well, it gives us this expression, right? And that gives me 2Ri delta R plus delta R squared. And so to a pretty good approximation, we could just drop off this delta R squared is going to be pretty small, so we could just ignore that because it's like 3rd order small. And we'll just have 1/2 times 2 giving me just 1 Ri delta R delta theta, And so the sign volume over z equals f of xy is approximated by, well, of course that's the integral over the region R, but we could write that as the sum I equals 1 to 3, because I actually had 3 in my toy example here. J equals 1 to 7, and then I'm using x sub I star, y sub ij star as like sample points. Pick some points in the ijth region to evaluate the function. That'll fix the height, if you can imagine the height, these kind of like coming out of the page, if you will. And so we're, if these were all, if the f of xy was positive over the whole region, we'd be calculating the actual volume of that like skyscraper over this region. I don't know, maybe you could, like, the height of this one's this, right? And then the height, oh man, I've only got, see, this isn't going to work because all I've got is markers of the same cap height. If I had different cap heights, this could be really awesome, but oh well. Sorry, I only use Crayola markers, what can I tell you? Because they're cheap and they work great. But anyway, so to a good approximation, the sign volume of f over this region R, we can get from taking the sum I equals 1 to 3, j equals 1 to 7, f of appropriate sample points times the area of the ijth region, which to a pretty good approximation is exactly this. And I'm saying, okay, well, I really should think about rewriting the sample points in terms of corresponding sample points in the radial or theta. So like here, Rij, theta ij should be an element of the ijth area, right? And you can pick them however you want. You could pick the sample points to be, like this corner in every one if you want. Or I guess that it doesn't really matter. You could pick the sample points however you like. Just like we could use the left or the right or midpoint rule for single variable integrations. It's the same kind of story here. In terms of the approximation, you could pick the approximating points however you like. But then the point is as we imagine more and more and more and more subdivisions, if we imagine the number of sectors going to infinity both in the radial and the angular sense, then of course delta r and delta theta shrink to 0, further motivating me ignoring that term because it's super tiny compared to everything else. And so we get this integral actually not being an approximation, but actually being equal to the limit as m and n go to infinity of this summation, right? But then the thing is, if you remember our definition of double integral, this is exactly the integral of the function f composed with the x and y functions parameterized by r and theta for the region times r dr d theta, and the integration region being r min, r max, Cartesian product with theta min, theta max. So what we're seeing is that to calculate this integral in polar terms, we have to do two things, not surprisingly. We have to change the integration region to rewrite it in terms of polar coordinates, right? That's changing the bounds. And we also have to change the measure. Where we had before dA was dx dy, corresponding to like the area being delta x delta y. Well, now with the polar approximation passing to the limit, we pick up this r factor, interestingly. And so another way to package this is just saying dA is r dr d theta. All right. Now, so this is the change of variables theorem for polar coordinates in the case that the region is relatively simple like that. All right. So let me move on here. So, I forgot to say, we're in pages. This is based on pages what to what. I should have brought my glasses. I can't see anyway. 295 to 307 of the 2020 notes. I can't spell. Apparently I forgot 2020 is 2020. Anyway, sadness. All right, so the next few pages of notes I work towards deriving, if you will, the result that we just saw an example of for sort of a more arbitrary coordinate change. And so the basic idea is we're going to trade x1. We have Cartesian variables x1 through xn, and we can rewrite those in terms of another set of coordinates u1 through un. And these are interchangeable. Like you can either write Cartesians in terms of the other coordinates, or you can write the other coordinates in terms of Cartesians, right? Both this perspective and that perspective matter. We've already seen this with like our previous discussion of polar coordinates. We can either write x equals to r cosine theta, y equals to r sine theta, right? That would be analogous to this line. Or analogous to that line, we could write r is equal to the square root of x squared plus y squared, and theta is equal to the inverse tangent of y over x, right? Good coordinates are invertible in that sense. Now, so here this paragraph discusses some subtle points. Basically, the coordinates are not, strictly speaking, invertible. There can be defects like the angular degeneracy, and essentially the coordinate systems we use have degeneracies which aren't going to be picked up in the integration process. because the degeneracies of the coordinates tend to be lower than the dimension we're integrating. So like when you're integrating over an area, the degeneracy is like a curve, so the integral is insensitive to that. I'm not really doing that idea justice. I just say you should be aware of coordinate defects and the fact that if you could probably come up with a sufficiently malevolent example to make it hurt you. But you have to work pretty hard to come up with that example. Usually the fact that the angle's not defined at the origin, for example, does not keep you from doing integrals to the origin with polar coordinates, as an example of that degeneracy I'm talking about. But anyway, let me get out of the weeds here. So here's an example. If you have a transformation, x equal to AU, y equals to BV, then what that's going to do is it's going to take the unit circle in UV space and transfer it over to this ellipse in XY space. All right. So this transformation takes a disk and squishes it to an oval. And so essentially the idea is to study functions of several variables. We can study how they act at sort of the infinitesimal level in the same way. Like a transformation, a linear transformation, is going to take something like a rectangle and maybe squish it out to some kind of sector. But if we get down, that's still at the macroscopic level. If we focus in further, down, we can just always think about rectangles going to parallelograms, actually. And there's a nice theorem that, and so this is pretty nicely treated in what it's called Vector Calculus, written by Susan Culley. This is in its 4th edition now. You can get an old edition pretty cheap. If you're interested in this level of discussion, I think she has probably a better treatment than in these notes, and it's a little bit more careful probably. It's a good book. Anyway, essentially this is the result. If you have a parallelogram and you map it under a linear transformation, actually this is an affine transformation because there's a shift by a constant, then the area of the transformed region is the determinant. Let's see here. It's the determinant of the transformation times that transformed area is equal to the area of the yeah, good grief. I've lost track of which is which. So no, D star is not the transform. So the D is the transform. The area of the transform parallelogram is the determinant of the transformation times the area of the original transformation. And so essentially, if you apply that at the infinitesimal level, well, this is so if we think about delta x and delta y being very small, even for a a curvilinear transformation, well, the area of the transformed rectangle is, or parallelogram, ends up being just the determinant of this particular matrix of derivatives times delta u delta v. Well, anyway, I'm sorry, I'm not doing it justice here. It takes me a lot longer to really talk through this properly, and so my apologies. I don't think I'm doing a very good job at the moment. But this is essentially the point: is that if we have a curvilinear transformation, then we look at it, its linearization. Then we can study how that linearization is taking a little rectangle to another little parallelogram. In this case, and the area of that parallelogram is given by the determinant of the Jacobian of the transformation times the change in the variables, like that. And this, it works as well in 2 dimensions as it does in n. In fact, the area of an n cube or whatever squishes to the determinant of the transformation times the change in the transformed variables. And for 3 dimensions, it looks like this. And so, long story short, what this is saying is that to change variables, we have to change the measure, which I usually call dA or dV, and to do that we just calculate what's called the Jacobian determinant. So for 2 dimensions, the Jacobian determinant looks like this. We just partial x, partial u, partial y, partial u, partial x, partial b, partial y, partial v. Take this difference here. So like here's an example. polar coordinate change. We've got u equals to r cosine theta. Well, excuse me, x equals to r cosine theta, y equals to r sine theta. So here u is r and the v is theta, so to speak. So the Jacobian, partial xy partial r theta, is determinant. It's the determinant of that 2 by 2 matrix, which x r cosine squared minus a minus gives me plus r sine squared theta is r. Hey, that's exactly the r we saw back over here. That's exactly this this r down here, if you will. See, this r is the Jacobian of xy with respect to r theta. That's the significance of that r. Here's another Jacobian calculation. If we have x equals to 5u minus 5v minus v and y is equal to u plus 3v, we can calculate the Jacobian. We get 16. If you had this transformation, you get that Jacobian. All right, great. If you had x equals to alpha sine beta and y equals to alpha cosine beta, you can calculate the Jacobian and get minus alpha. There's another handy-dandy theorem here. This is actually sometimes very useful because it's not always possible to calculate x as a function of the transformed variables and y as a function of the transformed variables. Or sometimes it's just easier to look at the transformed variables as a function of x and y. And so like partial xy uv is also the reciprocal of partial uv with respect to xy. Let's see here. So, well, I don't have a good example of this, but I'm just telling you this proposition is super, super useful for certain homework problems. And when you get stuck on it and ask me an email, we'll figure out which one it is. All right. So finally, getting to the point here, eventually. In terms of our, basically we're saying that we can rewrite the dx dy as partial xy partial uv du dv. And so this is how we change the measure of the integrations, kind of, so to speak. But it turns out when you get into the details here, you need absolute value. Because it can be that you get a minus. This is a determinant, right? So if you switch the order of u and v, you get plus or minus what you had. You get minus what you had if you switch the order of u and v. So that minus is not something that actually the integration should care about, right? Because this is integration where you could either set it up xy or yx, right? That's the Fubini result. We could set up the integral type 1 or type 2, so forth. So definitely we need absolute value there. And so here's the theorem. If you have a transformation that's mostly invertible, except possibly on the boundary, that's supposed to be type 1. I got type T. I don't know how that happened. Type 1 or type 2 region S to a type 1 or type 2 region R, and suppose that f is a continuous function whose domain includes R, then we can trade the integral of x and y with respect to x and y over R for the corresponding integral of x and y rewritten in terms of u and v times the Jacobian, absolute value of the Jacobian actually, determinant of xy with respect to uv du dv. And that, my friends, is the change of variables theorem in 2 dimensions. I have not proved it. I've tried to give you some somewhat motivating arguments. I probably haven't done a very good job. And to be honest, the proof of this is actually quite involved. To really do it justice, it would take a while. I don't think it's an exaggeration to say that the general proof of this takes about 70 pages of one good book I have. Not just the proof, but the setup of the proof, the doing everything that's required properly, because it really requires the study of volume in the abstract to do it for n dimensions in the proper way. I think a good proof of it's actually found in Muncre's analysis on manifolds text. All right, so let's apply it. So the integral of xy, f of xy dx dy, we could trade for the integral of f of r cosine theta, r sine theta, times that, which is just r. So like this is just the generic game plan. If you want to change the integral from xy to r theta, you do this. So there's this funny r that just appears seemingly from nowhere, but it's not from nowhere. It's because when we change the approximating regions from rectangles to sectors, we pick up an r factor. Now, for example, if we wanted to calculate the area of a circle, integral over the circle, rather the disk I should say, radius a, then we would integrate r d theta over s. Now s is the transformation of the circle from Cartesians to polars, and so in polar coordinates the circle is just 0 to 2 pi crossed with 0 to r. Of course, I put theta first and r second. That's I should really put them the other way around. Oh, and it's radius a. So oops. Oh, the region I'm calling r. The radius is a. I'm an idiot. Anyway, so when we do an integral over that, I chose to integrate over r first, which goes integral from 0 to a, r d theta, and then so what a pi? What's that? Excuse me. Come on. What is wrong? 2 pi. Come on. Good grief. And so you get 1/2 a squared from that integral, and the d theta integrates to 2 pi. The 2 and the half cancels, and we get pi a squared, as we should hope, right? If you do this example, I think if you go back in my notes, golly, I'm trying to remember. Well, anyway, if you do this in Cartesian coordinates, it is much more difficult. It requires trig substitution and the rest, right? Now this next example, it calculates this integral by an appropriate coordinate change. So this kind of so the previous example, it was the integration region that it was kind of is a circle, right? So use polar coordinates to treat a circle naturally. This next example, it's the integrand that's kind of in the driver's seat. So here we've got this rather ugly looking expression in the integrand, and the trick is to introduce variables which make this integrand something relatively simple. So what I do is I let u equal to x plus y, and I let v equal to y minus 2x. And in so doing, this becomes the square root of u times v squared, which is, that's easy to integrate in terms of u and v. And so let's see here. I took these and then I solved for x and y. That's a little bit of algebra right there, right? And so my transformation is such. And then on the next page, I show what happens. The original integration region, if you look at the bounds, they were from 0 to 1 minus x and from 0 to 1. So 0 to 1 minus x is like type 2, and then x goes from 0 to 1. So this was the integration region, and the transformation is a linear one in the sense that x and y, or u and v, are both just a linear combination of the other variables. And so linear transformation takes lines to lines. So like actually, if you wanted to, you could have just played the game of move this point, and this point under the transformation to this point, and I don't know which one went to where, but the other two go to these two, and then connect the dots, and that would get it for you. So this triangle maps to that triangle under the transformation, and I actually went ahead and transformed the equations of the boundary under the transformation as well. And so yeah, there's starting to be some noise in the room outside my office. I don't know what's going on. Sorry if I'm distracted. And anyway, so we get this transformed region. So we can trade this integral over that triangle for an integral over this triangle. And but to be fair, we also have to change the measure. And so that you have to calculate the Jacobian. So we do that here. Take partial derivatives of this formula here and that formula there. So that's why I get like partial x partial u is 1/3, partial x partial v is minus 1/3, and partial y partial u is 2/3, and partial y partial v is 1/3. So partial y, partial v. Oh, right there, yeah. And so that works out to 1/3. And so put it all together and use the change of variables theorem. We trade this ugly integral for this correspondingly simple integral, root u v squared, which integrating with respect to v gives me 1/3. And that's supposed to be a v, integrate v, that v squared should go to cube, right? It should be a cube. V integral v cubed over 3. I got the 3 right? And square root of u dv, well, wait a minute. Wait a second here. What happened? Where did my... What? Oh. Well, this down here, how did I get a 9? Oh, that's from the Jacobian. Listen, I think the easiest way to fix this is just to cross that out. That's just, there's got a couple problems on that equation right there, so let's get rid of that. And then going from here to here is right. The ninth, we get a v cubed over 3 from the integration with respect to v. We get a 1/3 from the Jacobian, and the square root of u just rides along. We have to evaluate from minus 2u to u. Okay, that's good. And so then we get this, and then of course that gives me a minus 8 plus, but minus minus gives me plus. So 1 plus 8 is 9. 9 over 9, 1, so that's why the 9 goes away. And we get u to the 3 plus 1/2, which is 9. What? How did I get? Oh, 6/2. 6/2 plus 1/2 is 7/2. 7/2 plus 1 is 9/2. So u to the 9/2 over 9/2, which is 2 ninths u to the 9/2. Come on. Which gives me 2 ninths. So there you go. That's I think that's about the toughest example I can think of. You know, that I don't know. The other examples always requires a certain amount of finesse, but next example here is with polar coordinates, and let's see here. I'll pick up right again here.